How are we doing? Okay, good. We're doing great. All right, so we talked about how to append and how to at least print it out, so that looks good. If we want to iterate through, we have a current here. We called it rover, and it can move the way through. All right, good. I want to be able to search, insert, and delete. Did I assign inserting in here? I don't think I did. That would be annoying. I decided to insert. Bless you. Wow. And I assigned if their two are equal to each other's, but I didn't do search. But I have insert and remove. Okay. So let's first talk about insert and delete, and we'll talk about search, and then we'll think about which one we want to implement. So we talked about traversal. We actually coded that really fast. So they used current. I did rover head. While it's not null, keep going to the next. All right, great. And this is how you could print it. We have a definition of a node already. That's great. New node, head, and then at the end. All right. So let's say you wanted to insert P. Let's see, insert a new node with info 50 after P. So in other words, you want this guy to be P. So you have P new node. Why are we doing it this way? Okay. And we want to insert basically 50 between 45 and 65. How would we do this pictorially? Well, you just move the arrows. So here's the idea. Here's the first list, 45, 65, 35, 76. Our new node's over here. We're going to give it the value 50. So we place it here. And then, actually, they want the 50 to come after the 65 is what they're doing. And then that new node, its next will point to 35, which is P's next value. So new node dash next equal to P's dot next. That way it updates to this value. And then you have P's dot next equal to 50. So now we have this value inserted into the array. Or the linked list, sorry. Y'all see what's happening here? Use 2 pointers to simplify the insertion of the code. If you had P equal to what's previous and Q to what comes after it, then you just have the new node's link equal to Q, and then P dot next link equal to the new node. So Q comes up here, you're saving that out. P dash next goes to the new node. All right, fine, the new node goes up to where Q is. If it's easier for you to code it that way, please go ahead and do it. Deletion, what do they want to do? All right, you literally move the link around. So if you want to delete 34, whatever's previous, you just take that next and you go and move it to the next. And that deletes it.
That's link name.
Yeah, P-link, aka P-mnext equals to P-mnext.
Skip over it.
Just skip right over it. What else should you do though? Since this is,
Delete the node.
yeah, you want to delete that node, otherwise Valgrind's going to start yelling at you. There it is. Don't forget to delete it. Yep, there it is. Have the 2 pointers, P jumps right over it, you delete Q, we're done. All right, you can build a linked list by always appending to the front or in the back. Right now we're always appending to the back. That's just for what we did today. If the data is unsorted, the list will be unsorted. What if you wanted to keep the linked list sorted? How would you do that?
You use rover.
And then you find where it should go and put it there. Yep. Okay. All right, we already talked about building a list. Doing great. Oh, okay. What would actually make our append work a whole lot faster? Picture here is showing you. You have head right here. What else could help make everything a lot quicker?
Tail?
A tail, because the tail is going to point to the final node. So if you maintained a tail, you could always just append real fast to the end, and then we're done.
Oh wow.
Yeah, wouldn't that be great? That'd be awesome. Let's go do that. So we have mHead. What do we need to add? mTail.
Wait, should it be a pointer?
Yes, it should. Well, that'd be bad. All right, let's go up to the top. Make sure it's initialized. What should mTail be at the very beginning?
No.
All right, mTail equals null. Wow. All right, let's go down to our append. We create the node. That doesn't change. If the node is empty, we set the head. What else do we need to set? mTail equal to
No.
to null. Its tail needs to point to the last node in the list. If there's one node in the list, what's the last node? Yeah, the first one, which is mHead. Perfect. And I'm going to shorten this up by just putting mTail at the beginning. All right. So now we need to first get a pointer to the last node. Hey, wait, what's that?
What?
We need to get a pointer to the last node. What does that happen to be? All right, so we can just get rid of this. So we have mTail dash next equals to the new node. Okay, what else do we need to do? Looks good so far. Let's go test it. Oh, seg fault. Wow. Do we still have our old error in there? Nope. So we're getting a seg fault. Whew, that's not good. So obviously our code's wrong. Let's see if we could run main. Not good. Seg fault. Oh, we're getting.
So, the seg faults when it tries to get to.
Well, notice the first print is empty, which is good. The second print is just 17, but the final print only prints 17 and 9001. It doesn't print anything else in here. So obviously something is wrong. Do we need to do something to mTail at this point?
Because we're not iterating earlier, we're just going from the beginning to the end. So we took out row conflict.
All right, so let's go map this out pictorially, because that'll definitely answer our question. All right. Seventeen's up here, and tail points up here, and the new node will go over here. Is what's it, like 8? We'll say 8. Okay. All right. So let's go look at our code real quick. Let's see what it's doing. And create the new node up here. That's what happens. mHead's not null, so we're going to the else, and we're saying mTail.next is the new node. Okay, y'all see that that's the line of code we need to execute? All right. So what does that do? mTail-next goes to this new node. All right, are we done? What are we forgetting to do?
We need to change.
Is mHead pointing to where it should be at this point?
No.
Yes, it is. That's the first element, right? It's pointing to the first element. Is mTail pointing to the last element?
No, it's not.
No, it's not at all.
Yeah, it's not.
Oh, so we need mTail to point to this guy, right? Right. So we need to set mTail equal to something. mTail equals new node, yes. Because once we do that, then we'll have mTail now point to this node. All right, is that good? All right. Oops. All right, let's go see if that fixed everything. Oh, that was it. See, wasn't that nice? Pen test. Oh, okay, you're good now. Isn't that great? Why was the there?
Nothing. Just, you know, just,
All right. So we added a tail. Now, how efficient is append? Beforehand, it was O of n. What is it now?
1.
Yeah, O of 1. So now adding to the end is O of 1. So adding something is an O of 1 operation. In an array, it could be O of 1 or O of n, depending on the situation. All right. All right, what do we have? Building a linked list backwards. We're not going to talk about that. Do we have anything else? We're not going to do iterators. Those are terrible. Oh, yeah. We never ran Valgrind. Let's go look at that. Definitely lost. What did we forget to do?
Delete new node.
All right. So we're over here, singly linked list. What do we need to do to delete everything?
Just delete new node.
So we just have a list. It could be of any size. How do we delete it?
Delete every element.
Delete every element. So what does that mean we need?
Rover again.
Rover.
Can't just say delete.
Well, okay. What happens if we delete mhead? We could try that. So beforehand we had 16 and 80 bytes, and now we have 16 and 64 bytes. All right, that's an improvement.
Sweet.
All right, that was not it. So let's go ahead and create that rover. Okay. What do we need to do?
Delete inval. Oh, we get an increment each time you delete inval.
So we need to set up rover going through the list first. Probably let's start there. C++. Okay. Rover's rover.next. All right.
So you need to delete something before you move over.
Okay, yeah, we do need to delete something. What do we need to be deleting?
Wherever it's at.
So we need to delete rover.
Where's
Mm.
rover.inval?
Rover.mval is just the value contained at the node. We need to delete the actual node, which is what's stored in memory. Remember, we were creating nodes in memory. So the whole node is memory, so we need to delete the whole node. Yes.
Which will start at the head.
Correct. And the rover starts at the head.
Oh. Sorry.
No, you're fine. Good question. Sounds like we.
Not start at the head, start at the next element.
All right, let me help you out here. Let me help you out. We'll create a node called delete me. Very descriptive, I hope. We'll have delete me equals rover. We'll move rover to the next, and then we'll delete me. That way, rover automatically goes to the next element. Then we delete the previous element, which is delete me in this case, and then rover keeps moving on.
So, deleting deletes both value, it deletes the whole node.
It deletes the whole node. It deletes a node.
Gotcha.
Yeah. And we define the node as containing the value and a pointer to the next node. So it deletes the whole thing. Okay. What is a good programming practice to do at this point? Although not required by, I guess, the semantics of the situation. Comment. Let me answer my own question. We should set mHead equal to null and mSize equal to 0 because we've deleted the whole thing. This is just good programming practice in case for some reason you start using these values somewhere else. You're in the destructor, so that should not ever happen, but it's good practice to go ahead and zero it out, just in case.
What about mTail?
Good catch. And mTail as well.
Could you ever execute something after a deconstructor?
No. Well, maybe. Depends on how complicated your code is. But you should not ever. But this is good programming defense, especially if you're just trying to get your labs to work. Yes, Jonah?
I said it depends.
It depends. Good question.
This should be the slogan to the class.
It depends. All right, let's go ahead and make it. Let's Valgrind it now. Hey, everything was freed. All right.
It's fine.
What's that?
Nothing. Have you been using nude? It's fine.
All right, let's go ahead and make our pen test to make sure we didn't break anything. Okay, good. We're still good. Okay. So that's how you destroy the list. Initialize the list. We already did that. Printing the list. We did it. Length of the list. We did it. Retrieving data from the first or last node. Well, you can just return mHead if you wanted to, but we're also doing that whole subscript, sub0 and sub whatever to actually get to the first and last node. Begin and end to iterate. We did that, copying the list. All right, we're not.
So to get the last node,
Let's do that.
you have to iterate through the entire thing and find.
Or we have mTail, so you could just use mTail to get the last element. You weren't here for mTail. We just added a pointer called mTail so we can keep track of the first element, the first node, and the last node. And that's why appending is O of 1 now, because we just append to the tail. But we have a deep copy constructor. Let's see, how can we do a deep copy? Let's see if we can make this easy for ourselves. You want to make this easy, Jonah?
Sure. Come forward.
So, we're starting off with an empty or a new linked list.
You
So,
could bracket keys or whatever. I saw it on the list.
yeah, we sure do. We'll have mTail equal to mHead equal to mTail, which is null. All right, and we want to do a deep copy, aka copy everything from one linked list over to the new one. How can we do that?
Create a new.
Create a new.
Do we need to go ahead and create a new linked list?
We are the new linked list that we're trying to create.
So we've been past one, so we just need to iterate through and add each element 2 layers.
Okay.
We just need to append it, don't we?
Yeah. So we need first. Let's iterate through. So we'll get the. And how do we do it? Well, we do that with a rover. So we'll start at its mHead while rover does not equal null. Rover equals rover dash next. All right. And what do we need to do every time we visit an element?
Append it.
Okay. So we need to. How do we do that?
Or you could call append.
Yeah. So this append, and what are we passing to it? Oh yeah. Why would we be able to?
Did value at rover?
That would be the easy way, right?
Yeah.
Yeah, just reuse the code we've already written. Wouldn't that be great?
Seems to
That's
be.
why we didn't do it.
No. It's called using your resources.
That's why I said it.
All right. Well, that seemed way too easy. Probably because I typed it real fast. Wonder if it works. Do you think it works?
I hope so. That's what I say to myself every time
I hope this works.
Nate.
All right. Then we'll do sl2.print. Let's see if it should. Well, print that off, create a new one, and then print it again. Let's see if that works. Make. Oh. Has no member next.
Oh,
Yeah. I mean.
yeah.
All right. Well, that was an easy one. Let's try it again. Ooh, it compiled. Drum roll, please. Nope. No. Hey, look at that.
Yay.
Wow.
This is great.
You see how using your resources helps? All right. Do we have any test for this? We have an equal test. Oh, we should do equals now. That'd be great. Be fantastic. Returns if the two lists contain the same elements in the same order. What's that?
Nothing.
We were talking
Could you,
about how great this class.
So how exactly do you use this?
This is just like in Java, where this is pointing to the executing object.
Okay, so this dot append means the current linked list that we're at dot append.
Call the append function on it. How do we find out if two linked lists are equal to each other?
Like the same values.
All right.
Same
How,
memory location.
no.
That's not true, right?
No, if they contain the same elements in the same order. Oh, see, I wrote that right there. How do we do that?
Iterate through, make sure that each position is equal, they're equal to each other.
All right, so what do we need?
We need two, right?
We need two rovers.
I hate myself for that.
What do you want to call it? Rover 1, Rover 2?
Or Rover and Dover.
Oh!
I was actually
Oh, that's great. Rover and Dover.
Isn't there a game that something like that?
All right.
Red Rover, yeah. That's right.
All right, so how are we going to test this next? While, let's see, Rover does not equal null. Woo, that's an interesting symbol. And Dover does not equal null. And what else?
And rover equal Dover.
Rover mval equals Dover. All right. So as long as that's holding, what do we need to go? We need to do. We need to iterate both. So
So how do you know when you should use this dot mhead or just use mhead?
this dash mhead and mhead are the same thing.
Okay, so
I only put this up there to make it explicit what it's talking about. It's the same thing. And I usually do that when I'm using two different variables that have the same name, just to make it clear which one's happening. All right.
So every time you use mhead or mval, you could use this dot mhead or this dot
Yeah.
mval.
And you mean this arrow, by the way.
Yeah.
Yeah. All right. So we do that. How do we know if everything's good?
If it returns true.
If it, what returns true?
The whole thing.
What whole thing? We're just
The
what,
function. It's a boolean, isn't it?
yeah. So we need to return true. When do we return true?
Oh, when their tails equal each other?
What would Rover and Dover be at this point if the two lists are equal? Hmm?
They'd be the same.
They'd be.
Oh, yeah.
They would both be null.
They would both be null. Because if one wasn't null, then it didn't get to the end of the list. So we're going to return Rover equals Dover, which equals null. Any questions?
Couldn't there be a situation where, say both were 6 linked and the first 5 elements were the same and the last element was different?
Yes?
So couldn't there be, could there be a situation where,
You know what? Let's write that test case. Oops, that's not what I meant to do. All right, let's go ahead and get over here with main. Let's go ahead and, oops, am I doing a pen test? No, I don't want to do that. What's a good first test?
So you just check to see if they return that.
Yeah. Oh. What did I type? Oh, I typed Vim in front of it. That's cute. Ah. We haven't talked about the doubly linked list yet. Uh-oh. It's
Whoa.
not a template. Oops. Yep, don't need to template that. There we go. Use into error request. Wait, what? Alright, hold on. Clear. Phew. Alright, hold on. Null used in arithmetic. Why is that an error? I mean, it should be. Alright, we'll do it this way then. Okay, there we go. And we're okay. Great. That fixed that error.
Why is it in there?
Hmm?
Yeah, why was that an error?
That is a great question. Null used in arithmetic. So it's assuming that Dover equals null. Oh, because that's going to return true. Oh, yeah, that is an error. Because you mean to test each one of them separately to make sure they're null. What the first one was doing, that was an interesting error. Dover equals null would return 0 or 1, and then you're comparing 0, 1 to Rover.
Which doesn't make sense.
That doesn't make sense.
Okay.
So that was an error, which is why we didn't have a good success rate, because we're not doing it correctly. But now we're actually testing it correctly, so that's good. Good test cases helping us out. All right, so that was the first test case. Let's go ahead and add some values to it. S1.append, let's see, 17 and 27, and then we'll do the same thing for SL2. And they should be equal to each other, correct? All right.
Whoa.
That means we didn't change our test function name. We'll call it test2. That's what that means. Hey, doing great so far. All right, test 3. Maybe we'll have SL2 append 37. So then this should not be true, correct? All right, did I get test 3? Oh, we're doing great. And then that last test case you were talking about, where let's say,
the last values were different?
yeah. So they're the same length, but the last value is slightly off. And they should not be equal to each other, right?
Right.
Nope. Yeah, it was fine. Because the reason for that is if at one point at the very end Rover-null does not equal Dover's null, then it's going to exit out, and both Rover and Dover are not null because they're pointing to an actual node. So that's why this code works. All right. All
I
right.
guess the reason I was thinking about that is that on the last time, when you get to the last element that's not null, say if they were different, then when you incremented them both to normal.
Oh, but you would not increment them. That's the point. If they're not equal here, then you exit out of the while loop without incrementing.
Oh, okay, so it wouldn't let you in the last element.
Right.
Okay.
But that's still a great test case. Because someone's implementation probably would have done that. All right. So we are almost